Hi, this is Tim Fox, and this is the second video in my series about BigDL. And here we're going to look at first neural network in BigDL. A little about me. I'm a data engineering and data science practitioner and a partner and principal at Elephant Scale. At Elephant Scale, we do training in big data, AI, deep learning, and machine learning. And I'm an author of data science in Python on LinkedIn Learning and an open source contributor to projects such as BigDL. You can go ahead and clone our repo as well. You can see the repo here. Now I'm going to go ahead and show you the first examples here on BigDL. So I'm going to go to the notebooks directory, that's where I am, and I'm going to click here on the feedforward-iris.ipython notebook example here. You're probably familiar with the iris dataset. It has 4 input variables, which consists of the petal length, the petal width, the sepal length, and the sepal width. And we have 3 output classes, setosa, versicolor, and virginica. So in our output data set, we've actually simplified this data by simply making the classes 1, 2, and 3. As a matter of fact, this is one of the requirements that BigDL has, is that output classes should be numeric and they should start with 1. Here are our imports. So we have our imports here. We have our ordinary imports. We're going to be doing some stuff with sklearn and matplotlib and seaborn. We also have imports from BigDL. Now, here are several parameters that we have here. The first is our learning rate. Our learning rate is going to be basically the step size for our gradient descent optimization. We also have the number of training netbox, batch size, the number of inputs, number of classes, and the number of hidden layers. So let's take a look at this. So we have our learning rate is 0.1. We're at 20 training epochs, batch size of 16. We have our display step of 1. And we're going to have 4 input dimensions because there's 4 different variables there. 3 output classes. Remember, there's setosa, virginica, and versicolor. And we're also going to have 3 hidden layers. So here is a picture of what a simple neural network, feed-forward neural network, looks like. What we're going to do here, we are going to have an input layer. Now, the input layer is going to have as many neurons as we have input variables, which in this case is 4. Then we're going to have an output layer, which is going to be, for the case of a classification problem like this, we're going to use a softmax layer in which we're going to have 1 neuron for each output class. That would be 3 in this case. And then we're going to have some number of hidden layers. So in this case, we'll just do 1 hidden layer. And despite the picture here, we're going to be doing a hidden layer of size 3. You may wonder how to size hidden layers. So that is actually to be a challenge. As it says here, the best way maybe to do this is empirically. In other words, try different parameters and see how that goes. However, the best way to start may be using a rule of thumb like this. So if you look at this, we have some rule of thumb. And then basically it's going to take in the number of classes and the number of inputs, etc. And we're going to do this formula, which is going to then calculate what the size there of the first hidden layer would be. Now, if we need a second hidden layer, or in this case we're not going to have one, then we have another rule of thumb to be the second hidden layer. Now, in fact, actually I'll go ahead and implement these, and we will go ahead and run that. So you can see here that we have the hidden layer of 1 is 2.5 and 2.6, so we round that up to 3 because it has to be a whole number. Okay, so now we are going to go ahead and we're going to load our data into a Spark data frame. So we have the data here in data iris training and iris test, so we're going to make Spark data frames out of that. We're also going to coerce all the values to be doubles, so that way we just make sure everything is indeed a double. And then what we're going to do is we're going to convert that into, in this case, into an RDD rather than a data frame. Now, I'm going to show you another example later on in the video where I'll show you a example of using the pipeline API, which will in fact use data frames. But for now, we're going to look at the RDD-based API. So let's look at the training class distribution here. So we have 3 training classes, and we'll go ahead and run this. Notice here that the training classes, I do a matplotlib visualization on this, are fairly balanced. Apparently fewer versicolor than the other 2, but fairly balanced. Now, as for the validation class, we can take a look at that. The validation class is a bit more on setosa than the others, but there are very few numbers of samples in this data set. That's what we have. So let's go ahead and eyeball the data, see what it looks like here. So you can see here that the results, basically our results here, followed by, this is our values here, followed by our label. So using the RDD-based API that we're going to look at first, we need to convert this into an RDD of type sample. So sample is a special class that is within the BigDL framework and it requires data to be put in that here. So what we have here is I've actually written a little helper function that I have here that's going to convert an array to an RDD. It's going to take my 4 values and my prediction and put that into an RDD. And then I'm going to go ahead and have those RDDs and I put in the training count and the test count. So you can see here there's 120 items in the input RDD and 30 in the validation. So now we're going to go ahead and set up our network. Our network here is going to be a simple multi-layer perceptron model. You can see here we have a sequential layer. Then we are setting up a linear here with ReLU activation. And then that's going to be our hidden layer. And then our output layer here is going to be a softmax output. Softmax is usually used for classification problems like this. We're going to set that up as well. So here we have our input, our hidden, and our output. And so we're going to go ahead and instantiate that. And you can see as we instantiate it, it creates our layers here. Notice here it has a linear layer with a ReLU activation, and then the second linear with a softmax output. So now we're going to go ahead and we're going to do training our model. So here's what we have for that. We have our optimizer. In this case, we are taking our training model. We're setting up AdaGrad. We can, of course, use various kinds of optimization like SGDs, stochastic gradient descent, etc. We're specifying our learning rate and our learning rate decay. And we're also setting our validation logic here. We are going to be putting in the result data here as we're going in. That way we can view this in TensorBoard. So we're going to go ahead and run this. And you can see that the results took 11.4 seconds here. What we're going to do is we're going to plot the loss and the top one accuracy. Go ahead and plot the loss here. So we're going to use matplotlib to do that and get our running from our training results. And notice here that we have a steadily decreasing loss, which is good. And we look at our accuracy. And our accuracy is increasing. Plateaus near the end. So let's go ahead and look at that on TensorBoard as well. Now, to do this, we need to log in to wherever we're running. In this case, I'm running on Docker. So I'm going to go ahead and I'm going to paste this here. And I'm going to go to my command prompt. And I'm going to run TensorBoard here. Okay, I'm going to run that. And then I'm going to go over to TensorBoard. That's going to be on localhost 6006 in my case. So let me go to this. And it is localhost 6006. And you can see TensorBoard is here. So need to find our output, which is going to be find our output here. And we can see that the result here is this one here. Just unchecking my results that don't correspond to this. Good. All right. So I can look at this here. Here is my loss. So you see here my loss here is on the decline. That's good. Look at my throughput here and accuracy. Okay. We also can do a lot of other types of visualizations in TensorBoard. And, so there's a number of different types of visualizations that we can do. Okay, so let's go back to our Jupyter Notebook here. And we are going to look at the confusion matrix and the accuracy score. Now, the confusion matrix is going to show us how we actually did in our results. So we have a visualization of this here. So you can see here in this case, we have an accuracy of 83.3%. We had some misclassification here. Now, I would probably want to maybe run this a few times in order to get some better results. These 5 here, these are some misclassified results. May want to try adjusting some of the parameters and other things we have there. to get a better accuracy. But you can see here that in in most cases we got those right. Okay, we're also going to look at our results here as well. I showed you the example here using the RDD based API, but I'd also like to illustrate how to do this using the pipeline API, which is going to use the data frame based API. Okay, and to do that, we're going to look at Feedforward Iris Pipeline. So, same data set. So we see the same types of input variables, and our imports are going to be fairly similar here. We're going to use very similar input variables. We're going to size the hidden layers exactly the same. So now what we're going to do is we're going to load the data into data frames. And just like we did before, but instead of converting it to RDDs, what we're going to do is we're going to do a pipeline that's very similar to what we would normally do in a Spark ML 2.0 ML machine learning pipeline. Those of you who are familiar with Spark ML lib, this should be second nature to you. So we're going to use the vector assembler class in order to create vectors based on our input columns. We're going to use a standard scaler, which is actually going to go in and scale our inputs in order to have those in, apples to apples in terms of their magnitudes. Then we're going to set up a pipeline with our assembler and our scaler. We're going to go ahead and we're going to fit that to our training data set. And we're also going to fit our test data set here. So here's what that looks like. You can see here is our feature vectors that we have there. And we're also going to have labels there. Remember, the labels are going to be between 1 and 3. So now we're going to end up using the pipeline API to set up our neural network classifier. So to do this, we're going to go ahead and we're going to set a BigDL model. We'll use a sequential, and we'll add, just like we did last time, we'll add a linear layer with a ReLU activation, and we'll have a linear layer here with softmax. And what we're going to do is we're going to set up the DL classifier class, which is going to be our pipeline API way of doing this. And we're going to set their feature size is equal to our number of inputs. We're also going to set our label column, which is going to be this label column here. And then we're going to fit that to the results. Okay, so then we are done training. So now what we're going to do is we're going to take the output and make it a data frame object. So we're going to go ahead and do that. And then we're going to look at our results and show that. So you can see here, this is very similar to what we would do in a Spark ML. A result, you can see here we have our input columns, our label, our assembled column, which is just the vector assembler result, then our features, and finally a column called prediction, which contains what we are predicting the output to be according to the label. Okay, so now we're going to evaluate our model just like we did before. So to do that, we're going to use some classes here from Spark ML. That would be the binary classification evaluator and the multi-class classification evaluator. And we calculate the area under the precision recall curve, which is 1 in this case, 93.3 for both precision and recall in this case. We're also going to look at the accuracy and the confusion matrix. So we're going to go ahead and we're going to get that here. We're going to calculate the prediction accuracy. And we're going to do the heat map there as well. So you can see in this case, we actually only got one misclassification, which is right here. So oh, actually we got two. This one here and this one here. Yeah, so the total accuracy then is 93.3%. Great. So far we've seen the same simple example, the Iris example, both with the traditional RDD-based API as well as a Spark ML 2.0 pipeline API. If you're like me, you find the latter very exciting because it fits right into the type of machine learning work that we've all been doing in Spark up till now. Okay, so now I know a lot of what you're thinking. You're thinking, Tim, you know, this Iris stuff is great, but we don't really need deep learning to do Iris. And that's totally right, actually. Let's look at a more interesting example here. And so we're going to look at a feed-forward example, still a very simple example, based on a credit card fraud. Okay, so now this is a data set here that we've been working on. It is a actual data set which is looking at PCA data, the principal component analysis, which basically means is that we have dimensions reduced into a number of principal components. And this is mainly done, though, not just for the purpose of dimensionality reduction, but also for the purpose of anonymization. So you see here that we have these dimensions, which we can presume are capturing most of the signal of the actual input variables based on the credit card fraud, but in an anonymized form. Okay, so let's go ahead and we will run this. So we have our imports here. Let's go ahead and do that. Now, we have a very large batch size that we're going to be using here. We'll use 10,000, and that's because the data set is very lopsided. I'm going to talk more about that. We're not going to get as good results as we'd like, and one of the reasons why is that we have a very lopsided data set. Now, in our Analytics Zoo repo, we actually show you some ways that we can handle that lopsided input a little bit more effectively. But, for the purpose of simplicity here, we're not going to do that. So, okay, so here we have our input parameters. In this case, we have 29 input variables, 2 output classes. It's either fraud or not fraud. And we're going to end up with 10 hidden features in our hidden layer. Okay. So we'll go through, we can do our same sizing rule of thumb. In this case, we get about 4 for the first hidden layer and 5.3 for the second. We're only going to do 1 hidden layer in this case. Okay, so now we're going to load the data, and we're going to load it into a data frame. You can see here we have that. And I'm going to do a describe here on the data frame to get some summary statistics on the data. Notice here that we have a time as well as values here. We have 284,000 input samples. We notice here that we have our class here. We have that the values here are 1 and 2. So there's our input data. Now, look at how lopsided this distribution is. We have the normal and the fraud over here. I'm doing a matplotlib here where we're going to do a bar chart which shows the frequency of the normal label and the fraud label. So you can see the normal label outnumbers the fraud label by a huge margin, which we hope this is the case in real life too. I mean, I would hate to think that fraud would be very common. It shouldn't be very common, and that's what we see here. Sometimes in the past, we do a random split on our data. However, in this case, because we're going to be training a model for forward-looking data, and we have time series data, what we may want to do is just to simply split our data based on a certain time. So, for example, we're going to get, in this case, about 70% of the data going from a certain point, and everything beyond that is going to be part of our validation data set. Okay, so since we're using the RDD example here, I am going to go ahead and do our array to RDD thing here, where at the end of the day, we're going to get our training and test RDDs from this result. Okay, so now we're going to set up our network. Our network is actually going to be the same as the iris example, just differently sized. So we have, remember, a input layer, hidden layer with ReLU activation, and an output layer. Okay, so now we're going to run our optimizer. So in this case, I'm actually going to be using SGD, stochastic gradient descent. I'm going to go ahead and I'm going to have my data stored here so we can view it in TensorFlow, etc. And then I'm going to now run this. And you can see the results. Okay, so you can see the results here. It took about 3 minutes to go ahead and run this on my machine. Your mileage may vary on that. Okay, so now let's look at the results. So I'm going to look at the loss and the top one accuracy. So you can see here that we have our loss, had a spike here, but is eventually close to 0. Whereas our top one accuracy here is ends up being around 99.9%. Now that may be deceiving though, actually, and I want to point something out here. 99.9% sounds great, and it certainly is. But let's look at our confusion matrix to see what this looks like. Okay, so we can see here that we have all of the not fraud examples were correctly classified as not fraud. So that's good. We got very good accuracy on that. However, on the ones that actually were fraud, we actually got more wrong than we did right, unfortunately. I think that what the lesson to take away here is that we need to come up with probably a somewhat better strategy to deal with the lopsided data set here. And so actually, we have some examples there where we can do that. We actually have a class to help kind of take care of that. And there's other things we can do in terms of the tuning the parameters on that. But that goes a little bit out of the scope of this particular video. I didn't want to belabor that point, but just that to point that out that that's what we have there. Okay, so that brings us to the end of this example. Now, for those of you who are saying, well, what about the pipeline API? That's really cool. Well, I actually do have a pipeline API example for this credit card fraud. That is in the Feedforward Credit Card Fraud-Pipeline notebook, and you go ahead and take a look at that as well. So for those of you who are thinking, hey, these are really simple examples, when are we going to get to the good stuff? Well, we are going to be doing some more interesting examples in the next couple of videos. But, we have to start here, and I hope that you enjoyed this video and that you'll enjoy your experience with BigDL. I know it's a framework that I personally am very excited about, and I hope that you are too. Thank you very much.